Most people think the only way to improve language models is to add more parameters. But the real bottleneck isn't scale, it's compute routing. That's why the industry shifted to mixture of experts. Instead of firing every weight for every token, MoE partitions your model into specialized subnetworks. When a prompt arrives, a lightweight gating network evaluates the input and routes it to only a handful of active experts. The efficiency comes from sparsity. You're trading dense matrix multiplication for conditional computation. The router uses a learned softmax over routing logics, but with a hard constraint. Only the top K experts actually process the token. This keeps inference linear relative to parameter count, not compute cost. But sparsity creates a new problem, load imbalance. If the router consistently sends traffic to the same experts, you get bottlenecks and underutilized capacity. Researchers solved this by adding an auxiliary loss function during training. It penalizes uneven routing distribution, essentially forcing the router to treat expert selection like a differentiable auction. The gradient flows through the routing weights, optimizing both task-specific accuracy and system-wide balance. The result is models that scale to hundreds of billions of parameters without the memory wall. If you want to dive into the routing algorithms, load balancing techniques, and recent optimizations in dynamic expert selection, the latest research papers break it down. The future of efficient AI isn't about building bigger models, it's about building smarter traffic control.